All right, hello team, welcome back. This is Kevin Leach for CS3276 Compilers. This is a video guide intended to deal with getting started with Cool for PA1. So remember, for PA1, you're doing a topological sort implementation in both Python and Cool. The first part, Python, that's due a week before the PA1C, which is the Cool implementation, so you get an extra week on the Cool implementation. Now, there's already a couple of starter videos for PA1. I went through the setup for Windows, for getting the reference compiler working there, and then there's a few videos on doing Python implementations, so that you can kind of see like how to get started with Python if you're not familiar. We go through a Dijkstra's algorithm implementation. There's also two other videos on Cool that were done by a former colleague. So when we co-taught the course with this other guy, Wes Weimer, so I'm reusing his videos since they're perfectly reasonable. He goes through a Cool implementation of DFS in two different ways, and I want to add a third way, perhaps with a little bit more detail, focusing on a pattern that I observed in previous semesters, which is students often will go, they will implement their own list class in Cool to do the topological sort implementation. Now, you don't have to do it that way. You could borrow from the other two videos or whatever. I mean, that's up to you. But I figured I would at least add this to have some additional background. Now, for this video, I want to also kind of maybe explain some of the decisions behind why Cool is the way that it is, just so that we can understand a little bit about like when you're approaching Cool for the first time and you're writing software in it, how might you want to convert what you already know from other languages to make it work in Cool. Now, I guess before proceeding, I also want to just remind you that in this class you are doing a compiler for Cool programs written in Python. So all of the code that you're going to be writing and turning in is going to be in Python. However, we want you to encourage testing. Indeed, the autograder is testing your compiler components against test cases that are all written in Cool. And so we want you to have that in mind. That's also just good practice for industrial software engineering jobs later. The predominant activity of software developers is testing. So we want you to develop that mindset. The reason that we're having you do a Cool portion of this for this assignment is because we want you to get in the habit of writing your own Cool programs that you can use as test cases for your own compiler. And so being able to write programs that use all of the different features that are available to you in Cool is a good habit for this class, but also, again, like I said, just for practice later on. Hopefully you will do that. Indeed, students have come up with very large test cases over the course of this semester for their own compiler. It's a good habit to have. So that's kind of the intent here. We want you to be familiar enough with Cool that you can write your own test cases. Now, what are we actually going to be doing today? Well, let's turn to the whiteboard behind me, and hopefully I will not block too much. So what I want to go through today is a depth-first search implementation in Cool. DFS, you've probably encountered it before in a previous class. This is an algorithm for visiting nodes in a graph in a particular order. Part of the implementation is kind of keeping track of which things you've already visited and so forth, and that will, while it's not exactly topological sorts, you could potentially use DFS as part of your topo sort implementation. So maybe this will make your life easier for PA1C. DFS, more concretely, takes in a graph as input, and it produces as outputs some list of nodes that are in some order, the order in which they were visited, which is depth first. What that means is, if I look at this graph here that has my 6 nodes in it, I might start at node A, and if I'm doing depth first search, I'm going to visit as many children as I can until I hit a leaf node. So I'll keep visiting, depth first. I'll hit C. C has no children, so I will visit it. In this case, I will add it to a list of visited nodes. And then I will return to B. I am doing depth first, so I still want to reach all of the children first. So I'll go from B to F, then F to E. E has no children. I'll visit E, then I'll visit F, then I'll visit B, and then I just keep going until I hit all of the nodes in the graph. All right. And so that's the intent. We produce a list that does that. So we're going to accept some graph structure as inputs, and for this implementation, we'll also accept a source node as input. So we're going to say where we're going to start from, and we're going to produce this visited list, and print it out to the screen. One thing that I might care about, and like I said, this reflects what I've seen before in previous semesters. You don't have to do it this way, but you could. Is to create a map, which is going to help us identify the parents-child relationships in the graph. And so I could have a map where I'm going to map a name of a vertex, so I'm going to map A to a list of all of its child vertices, so all of the nodes to which there is an edge. So for A, my node A is connected to B and D, and so in my map, I will map A to a list with the nodes B and D in it. Okay? So I could create this type of map structure, and as it turns out, some implementations of DFS can consume this structure fairly easily to work with. So we will do that in Cool and see how it works for us. Now I will just want to mention a few things before we actually get started in Cool, and that is Cool is, again, a language that's meant to be easier to write a compiler for than it is to write software in it. So it is a language that may be lacking in some of the features that you are used to. For example, there is no built-in dictionary, map, or list type. There's no arrays in Cool. That makes our lives easier if we're writing a compiler for it. But if we're going to write, an actual program in Cool, we might have to do a little bit more mental gymnastics to get all of the pieces in place. So it's great. You'll love it. So we'll have to, make a map class from whole cloth, and we'll have to, kind of approach this in an interesting way, I believe. Before I get started, let me pull up my notes here, just so I cover all of the things that I care to cover. Let's see. I want to bring up this file. And then I will switch over to this screen here and open it up. All right. Now, again, you could follow along in whatever environment you want, as long as you have the reference compiler set up. So you will need the reference compiler if you're going to, test programs that you're going to be writing in Cool. And so I've already done that for my system. So I have Cool, put into place in my system already. If you're interested in how to do that, we'll either chat about that in class, or there might be a separate video about doing that type of thing. But I have my reference compiler set up and ready to go, and so now I'm able to write some Cool programs. So let me go ahead and do that and just say, we'll do a DFS Cool folder, and I'll just name my file, dfs.cl for good measure. Now, this video is not really going to be an explicit Cool tutorial, although I'll try to explain some of the common pitfalls that I've seen before. But there are example Cool programs that you can look at available on the course website. The manual describes all of the syntax and various structures that you can use in Cool. So this isn't exactly going to be a Cool tutorial explicitly. I'll try and mention a few things along the way. The first thing that I want to do, though, is using Cool's comment syntax, put a comment at the top with my name in it and email in it. That will be good for me. Now, what do I want to do? So, using Cool's multi-line comment syntax, I will put down a few notes here. We want to do a depth-first search implementation in Cool. I am just realizing I should switch to the correct view. My apologies. All right, it's a good day. All right. So hopefully now you can actually see what I'm writing. So using again the double dash here is for a single line comments, and then this business with the parenthesis and asterisk, that's for doing multi-line comments. So I want to have a depth first search implementation ready to go. So how am I going to do that? Well, I need to do a couple things. I want to read in some graph structure from standard input. Now you might say, like, why aren't we reading from files? Or why aren't we doing command line options? Cool supports neither. It's great. There is only one way of doing input and output in Cool, and that is through standard input and standard output. And so no complicated file I/O and all that stuff here. There is just standard input, standard output. It will be phenomenal. So I need to have some way of reading in a graph structure from standard inputs. If you followed some of the other videos, you've seen how that goes already for Python. We're going to have something similar here. We're going to read in lines, probably an edge list of a graph into the standard input. Now the next thing is, again, I need to store it, store the graph in some type of data structure. Now you might think, well, surely we can have some type of dictionary or array or list. No. Cool supports no data structures out of the box. If we want a list or an array or a whatever, we have to implement it ourselves from whole cloth. So we will just, so if we want to have this type of data structure implementation, maybe, as I mentioned on the whiteboard behind me already, I might want to have some type of map structure that will map vertex names into a list of child vertices. Now, what does that mean? Well, that also means that I need a list structure, to store vertex names. Now, again, in contrast to more advanced programming languages with, templates and flexible types and all that stuff, no. We will explicitly have one type of list, and that will be a list of strings and nothing else. So no other like list of integer or anything else that's too complicated. Just a list of strings. We will have vertex names represented as just plain strings. So we need those types of data structures to get rolling in Cool. Now, after we have those things, well, then we need to, and we've read our graph into these data structure that we'll implement. Well, now we need the actual DFS implementation, which we might consult the Google for to help us understand how to do that. All right. So a couple things that we need to take care of. The first thing I recommend when you're getting started here is to just do like a sanity check hello world program to make sure that the reference compiler is working and all that good stuff. So in Cool, every program needs to have a main class. Class names are always, the first letter is always capitalized, and then the rest of them aren't. And that will make parsing easier later on. But that's the way that it goes. We need a main class, and we're also, because we want access to doing I/O, so we want to print things and receive things from standard input, we're going to inherits I/O. So I/O is a magic intrinsic built-in class in Cool that will give us access to helper methods for inputting and outputting data from the command line. So we're going to have our main class inherit from I/O. Within our main class, we need to have a main method. This is the entry point of the program. That's where it begins execution. Main should not take any parameters. Again, no command line options. Main will return an object, and then in our method body, we will have a single expression here. We're just going to put something on the standard output, hello world with a new line. Great. Now I need to end method declarations and class declarations with a semicolon. And now I just want to test it. What happens? So Cool on dfs.cl. Look, it works. I see hello world. It is working so far. Cool. All right, so now we have a place to start, and now we want to get started with these other data structures and reading things in from standard input. So what I want to do then is to start by reading things in from standard inputs. How do we do that? You might be tempted to say, well, you know, let me just do in-string and see what happens. And it won't work. The issue is, and this is kind of one of the first pitfalls that I've seen before among students, and indeed I'll run into this myself, I'm sure, as I finish, as I go through the rest of this video. And that is, every method in Cool is exactly one expression long. And so in contrast to something like, you know, C, where I might have, you know, printf, some stuff, maybe we have, you know, int x equals 5 plus 7, or 9, apparently, and I can have multiple statements. That does not exist by default with Cool. And instead, again, to make parsing easier, every method is exactly one expression long, and the method returns whatever that expression is. And so, you know, right now, what it's doing with this outstring is it is returning a void object. You know, outstring doesn't return anything; it just prints to the screen, so it's just returning nothing, which is a type of object apparently in Cool. If I want to have multiple expressions run in sequence, I need to tell Cool to do that explicitly by adding a block expression. What that means is just add some curly braces and then a semicolon to delimit all of the expressions, and then Cool will kind of run things in step by step. So I could do something now like in string, and it will ask for user input now. And now it's waiting for user inputs. I can type it, and then, you know, it goes to hello world. So wonderful. Now we've talked about blocks. Again, the way to think about it is I have one single block expression, which itself contains a sequence of expressions to execute. And so that's to make parsing easier later on, but that's a common pitfall. Sometimes you'll add curly braces, and then you have to remember to add the semicolons. So, you know, keep that in mind. All right. But just before I move on, I also just want to document things real quick. So need main class for entry points. Main is a method with no parameters and returns an object type. Use extra curly brace to indicate a block of expressions. All right, and now I want to collect my lines of input. And in order to do that, you know, what should I'll need a few things, right? So I want a variable, basically, to put each line in, and then I'll eventually add it to a list. And so one thing that I might want to start with then is to just, you know, have some type of string, and you know, put the string somewhere that might be useful. All right. So what can I do, or how do I do that? Well, in Cool we have the let expression. So I'll say let x is a string that gets the result of running in string, and then I say in to indicate that I'm entering a scope where x is bound. So I have x available to me inside of this in clause here. And what I'll do is I'll just have, you know, outstring of x, and then, well, that's it, because let also only takes a single expression. So if I want to do something more, well, maybe I need to add curly braces. And what I might do then is to have an outstring as well to do a new line. By the way, we're doing this because Cool does not let you concatenate strings on the fly like this. You have to do all of your print statements separately. It's great. All right, so let's see, does this do anything so far? So I'm trying to read in from standard input. I'm going to echo it back out, put a new line there, and then do hello world. How's that going to work? I'll just type something. Great, I type in my string. It echoes it back to me. So Goodbye world, hello world, great. So it's echoing back what I give it. Sounds excellent. So now I have a way of getting a line of standard inputs, and I will eventually need to put this into some type of list. What I might do then is have some type of loop so that I can keep doing this and read in what will eventually be some type of graph input. So before we do that then, I want to just really quickly create some type of basic graph as an input that we can feed into our program. And so I might just create this file called graph, and I'm just going to say I'm going to have two nodes. In this example, we don't have any edge weights. We're just going to have directed edges. And so I'm going to have one edge in my graph that goes from A to B, and that's going to be my graph. Doing DFS should be fairly straightforward. If I start at A, I should end up at B. All right. So I want to be able to read in, let me make that slightly more interesting. So I'm also going to have A goes to C, just so that we have two edges. So basically, every 2 lines represents an edge that goes into the graph. And so I want to read in pairs of lines at a time and do something with them. So how's that going to work? Well, right now I'm only reading in 1 line at a time. So maybe we should do something else. So maybe I should say, well, I'm going to read in the source node, which is a string that gets in string. And then I'm also going to read in the destination, which is also a string, which is also in string, then I'll sort of read in 2 lines at a time. And so I'll say, we'll make a format for expressing the edges real quick just to test. So I will do outstring, where I'll have the source, I'll have a comma and the space, and then I'll have the destination, and then to finish it off, I'll have the ending parentheses and the new line. And so now I should be able to see, a pair of nodes that represent each edge on the command line. Will this even type check? Great. So no parsing or no issues with compiling and running it. So what happens if I just feed that program in as inputs? Great. It's only reading in 1 pair, and then it's immediately going on. So now I need a loop structure and a way to break out of the loop to know when I'm finished. So how am I going to do that? Well, there are while loops in Cool that we can do. All right. So first I'll say read in 2 lines at a time to represent an edge in the graph. And now what I need is a while loop, and so there's not like a way of checking for the end of standard input explicitly or anything like that. We kind of have to roll our own looping structure. So what are we going to do? We're going to create another let binding. I'm going to create a variable called done, which is a Boolean, which is initialized to false in, and then I'll have a while loop. I'll say while not done loop, and I will put in indent those one more. While loops ends with the pool keyword. This makes parsing easier. And what I'm going to do every time in this loop is I'm going to read in 2 lines at a time. And now, instead of directly echoing it back, though, I'm going to say, if it doesn't really matter which one, if the source is empty, so if inString has returned an empty string, and that means we're done, we finished all of standard input, then I will say done gets true. And if we're not done, or if there's still stuff to read, then we will put all of this stuff in a block for the else. So notice, by the way, because I'm in a block here for the let expression, this whole thing is itself an expression that must be terminated with a semicolon, just to indicate the end of that expression within that block. So now what I'm doing, I've created a new Boolean. I have a while loop where I say, while I'm not finished, I read in 2 lines at a time. If I hit the end of standard input, so if I return an empty string, then I am done, and then I break out of the loop. Otherwise, I'm going to print it back out to the screen in this edge format. Now let's see if this will work. Parser error, syntax error, need near 39. What is on 39? All right. Oh, all right. So in the same way that while loops end with pool, if expressions ends with fee. That again makes parsing easier. So I have to indicate explicitly the end of the else expression with the fee token. There's still a complaint here. So I have my let binding where I've created a little block here. The block ends, and I have a semicolon. Oh, the semicolon is not necessary because I'm inside of this this loop structure, this whole thing, this let expression, is one big expression. It with a sub expression here, but it's from the while loop's perspective, there is one let expression here, and the entire thing fits inside of the while loop. So that's we're almost there, but the problem is, and I mentioned this earlier, the whole while loop though, and this let expression is inside of a block, and so I have to terminate it with a semicolon. Cool is great. All right, so now it's working. The DFS I've read in, again, remember my graph file has an edge from A to B and an edge from A to C. I have read those in to this through standard inputs, and then I just echo it back sort of one edge at a time. All right, great. So I now have edges that are captured as strings now, and now I need a place to put them. So before we move on, let's just make sure that we have all of the documentation we need. So remember, this is check if we're at the end of standard inputs. In-string will return an empty string if it's like the end of file, right? So if you're at the end of if you're at the end of standard input, that's what it'll do. So this is to break out of the loop, and then we'll leave a note for ourselves. So we need a to-do. Put this information in a data structure. All right. Now all right. So we'll leave that there for now, and we'll move on to, now that we've read things from our standard input, now we need some data structures. And I said that we're going to do a map and list. We're going to start with the list since I think that is slightly conceptually easier. And so here's how it will work. So we'll have a list implementation, which will support. So first of all, we'll need a string to store the current, to store each element's value, right? So we're going to do a list of strings. So in my list class somewhere, I'm going to need to have some type of string attributes to store that value. I might want to have a size method to return the length of the list. That'll be helpful probably later on. I will need some type of next pointer. So I want a next pointer to indicate the next elements in the list. Right? So you may have seen something similar before in a data structures class. We're going to follow something similar where we're going to have a next attribute that points to the next element of our list. We want to have an insert method to add a string to the list. we'll also want to have a contains function. Now, this isn't strictly necessary, but because it may be efficient, or it may be nice to know if a list contains a particular element. We may not want duplicates in our list, so we may want some type of set-like behavior in Cool, and so in our list maybe we want some sort of contains thing that will return a Boolean. Boolean if given string is in list. So I want some type of contains method that'll help us out, and basically we might check, is there a element in this list? Maybe that'll affect whether we insert a duplicate. Maybe that'll affect something about DFS if he wants to check if a node is in a visited list already. Could be useful. We may also want some type of remove method. Get rid of given string from list. And we might need a few other helper functions along the way. In my notes off to the side that I'm looking at, I don't want to borrow from the future quite yet, but there could be other helper functions that we might talk about that relates to making sure that the list is in a particular order. And also I'll just make a note here as well. We'll want to have some type of print method to help us print out a list. Print out a list. The final thing, and I think this is another kind of conceptual hurdle and a pitfall that is admittedly not the most intuitive. Cool does not have a notion of like a null pointer check. There's something like it. There's an is void built in, which can kind of help with that, but there's not really like a null pointer. And so when we're in contrast to a previous class where maybe you've rolled your own linked list structure, maybe you had some type of loop where you kind of check, oh, is this element null? If it is, I get to break out of the loop. And if it's not, maybe I do something else. If we want that type of behavior, we need to explicitly maintain it. And one of the ways that we can do that, again, you can compare this with the other two videos that are already posted about Cool, is we're going to want to have an isNill helper method to tell us if a given node is valid, or if it's an invalid cell that might mean it's the end of the list. So this is very common in functional programming. And so, for example, there's a structure, you can Google this if you want more reading. But from the Lisp programming language, there's something called cons and nil. And this is an approach to building up linked lists when we don't really have a notion of null pointers for doing this type of check. And what happens is you have some type of parent abstract list class, and then you have two child classes, cons and nil, and you use you check the type of the data structure to indicate whether it's a null, like the nil, an end of the list, or if it's a cons, which is a valid concrete string or cell. So we're going to borrow that type of setup. Again, there's more starter code, that example code at least, that has this structure as well, and you can read about it on Wikipedia. But this is kind of a different way of thinking. What's going to happen then in our implementation is we're going to have an abstract list class, and then we're going to have a child concrete ListNode class that will inherit from a list. And what this will allow us to do is essentially anytime we want to indicate the end of a list, we're going to have a list object. That's an abstract class type. It's not really a concrete cell, but it'll make it easy for us to check, like, oh, it's not really valid. That's the end of the list. And we're going to have, instead, the list itself is going to be made up of a sequence of concrete list node cells, and that's going to help us maintain what we need to know about the list itself. So we're going to have a list of list nodes that are terminated by an abstract list. So if I want, for example, to have the list ABC, well, the way that I'm going to do this is I'm going to have a list node object where I'm going to have, it's going to store, the first element, and then it's going to have some next pointer that goes to another list node, which has B in it, with its own next pointer that goes to another list node with C in it, and its own next pointer, which then goes to a list object. And that'll be how my list actually gets represented as objects in memory. Now this should be familiar to like the linked list, but again, it's just kind of this conceptual difference because there's not really a null pointer check that we can do, that we want to do, at least for this implementation. We're going to make a distinction by using a different data type, and we'll essentially have this helper method that will have a different return value depending on which data type we're in, and that'll help us distinguish if we're in a concrete node or if we're at the end of the list. All right. So let's get started. So how's this going to work? I can just add the class definition anywhere. For good measure, because I might want to print things out for debugging later, I'm going to inherit from IO just to gain access to the outstring and the instring method and so forth. That might help us out. First thing I'm going to do, I want to follow my notes real quick. All right, so I'm going to have an element in my. If I'm going to have a list of strings, then I need to have a variable or an attribute that actually stores the string that is contained in each element of the list. So I'll just do that here. I say, S is a string type. I'm also just while I'm here, I'm going to create an accessor method which returns a string that just returns S directly. In Cool, all attributes are private. There's no way to access them outside of the class or any of the child classes. In Cool, all of the methods, though, are public. And so if I want to access a particular attribute, I need a method, and you can name it whatever, but you can overload the name like this in Cool. So I have this method called S, which will give me the value regardless of which scope I'm in. And so I'll use that as a nice helper method. So all attributes are private. All methods are public. Need a accessor for private attributes. All right. And notice, by the way, like I mentioned this earlier, every method in Cool is exactly one expression, and the value that is returned by the expression is what that method returns. And so there's no explicit return keyword or whatever. I just say this S method returns whatever is in this S attribute, and that's it. Right? And so that's how that works. Cool. All right. So what's next? I might need some type of size thing, a size method that returns an integer for now, or perhaps we'll come back to this later. I'll say again, this list class that I'm implementing, this is meant to be some type of abstract class that doesn't really mean anything. It is meant to indicate the end of a list. And then I'll have another class that inherits from this later that has a concrete value in it. What that means is, if I'm getting the size of a list object, this is meant to be like the null pointer. It itself is an empty list, and so for now I'm just going to return 0. I'm going to say it's a 0-sized empty list. Again, we'll come back to that when we get to the concrete class implementation. I will also need some type of next pointer. So I'll have a next pointer called n, which will be a list. And so I'll just have that, and then similarly I'll have an accessor method for it that just returns n. Next pointer. All right. I will also want to have some type of insert method. Insert is going to take a parameter. I want to add a new string into this list, so I'll say new s is a string type, and what I'll do is, for now, nothing. We'll come back to this implementation later. But I want to have that insert method, I want to have a contains method. So I'm going to have some search string that's an input. Again, I'll come back to this later when we get to it. I want to have a remove method that takes in a parameter that's a string, which we'll come back to. And what I might want to also have is some type of print method. Print will return an object, and just for now, again, we'll come back to the implementation in just a second. The other thing that I've noticed, by the way, well, type in the chat if you can predict what's going to go wrong here. There's going to be a problem here because I haven't specified return types for these methods. So what I'm going to do is, and this is the next conceptual hurdle, in functional programming languages, some languages, regardless, you can do it this way. It's very common to not directly mutate a given object, and instead you always return like a new copy of the data structure, and that can make certain optimizations easier and certain correctness properties easier to evaluate. We'll get to that later in the semester with optimizations. But what I will have, though, for these, basically for all of these methods, I'm going to return, well, let me put this separate, but for insert and remove, these methods are going to return essentially like new copies of the list with whatever modification they need. And so these methods should return lists. And so we're going to essentially make these new copies of the list with some change in place. We'll establish how that's done in just a bit. But so this should now, I believe, type. Well, there'll still be other errors because right now, like this method doesn't do anything yet, and so we'll come back to that later, or we'll come back to that in a second. All right, so we have all the methods in place for this, kind of abstract class. This list class again is going to help us keep track of the end of the list when we reach it. Now remember, one of the other things that I put up here in the notes is that we need this isNill helper that's going to help us distinguish. And I want to use this as the point for distinguishing between this abstract list class and then this yet undefined ListNode class that we're about to implement. And so the other attributes that I want to put up here is an isNill method, which is a Boolean, and it is going to return true. So we're just going to say, if I ever encounter an object of this list class, that means it's the end of my list, and I'm going to use this isNill to help me make that distinction. IsNill will return true if it's an instance of list, and it's going to return false if it's an instance of the concrete ListNode class that we're about to implement. So let's take a look at that. Oh, and one more thing, contains should return a bool. We'll come back to that in just a moment. All right, so I've just I guess, laid out a skeleton for this abstract list class. Now I want a concrete ListNode class that is going to inherit from list. And this is going to be a concrete list element that contains an actual value. So this is going to be like an actual cell in the list, and I'm going to be able to use this to help me distinguish between the concrete list object and this abstract list object that I just implemented earlier. So I have another class definition here, and here right off the bat, the distinction here is for this class, I'm going to say isNill is false. This will be my indication that it is a concrete list element. Now, what am I going to do in this classes that might be different? There's I already have when I inherit in Cool, I get all of the attributes that I had before. So I already have, well, I've overridden isNill. I already have s and the accessor. I have this size thing. I need to override size, so that'll be a function that I have to implement in just a second. I need to implement the remove So I'll need to override the remove method. Here, which I'll implement as well. And one other part, and this is where we'll actually begin the implementation, because I think it's helpful to kind of help us visualize what's going on in this class. I need to have an init method, or I'm going to have an init method. This is going to be like a kind of like almost like a constructor. By the way, there's no like explicit constructor in Cool. It's just new, which allocates the correct amount of memory for it, but it doesn't actually run any code. So if you want to have a constructor, you can write one yourself with some unique method name. And so I'm just going to have this init method. It's going to take in some string as input, and we're going to also explicitly pass in some new next pointer, which will be a list type. This is going to return a new copy of the list. What am I going to do here? So when I want to add a new element to my list, I want to create a new concrete ListNode object that contains that value that I want to insert into the list. And so one of the first things that I'll want to do, this will be a block by the way, is I'm going to overwrite S with whatever new S is. So remember I have this S field up here. You know, all child classes have access to private members as parent classes in Cool, so we can totally do that. That'll be great. So I'm going to overwrite whatever S is. It should be nothing when I'm first calling this method. I will put in whatever that parameter is, and then also what my interface is that I'm going to expect here is that anything that creates a new ListNode object is also going to tell me what other stuff was in the list before. And so that needs to be passed in as a parameter, and I'm going to say next gets new next. This is, and this is again kind of a conceptual hurdle, because Cool doesn't really let us manipulate objects in the same way that you might be used to. We're going to return a new copy of everything. What this means is every time I want to add an element to a list, I create a new list node, and then I take whatever was already in the list and put it in as the next pointer. And so that's the interface that we're expecting here. That's what's going to happen with our init function, with our init method. Now the final thing here is I need to give a return type. In Cool, the last expression in a block, this will be what the return value is. This is wrong, because I want to return the whole element, the whole new list node that I've just created. I don't want to have my list start at the next node. That would be wrong. Instead, what I do is I just give self. Self is like the this pointer. The self pointer just is a reference to a copy of the current object that we're dealing with. So what we just did then, when we call this listnode.init method, we will put the new string into this new element, and then I'm going to add in all of the stuff from the previous list as the next pointer, and then I'm going to return a copy of this new list node, and that's what my init method is going to do. All right. How do we get there? So the way that we're going to expect this to work is our user is going to create some list object, and then they're going to start inserting objects into it. They're not really going to be interacting with the ListNode class. They're going to be interacting with this list class. They don't want to make our user, our developer that's using this class, isn't going to want to have to care about whether they're dealing with a list node or a list. That's supposed to be kind of transparent to them. And so in our insert method then, we need to actually provide an implementation that makes use of this newly created init method that we just put together. So how is that going to work here? Well, remember what I'll do if I ever want to insert an element into an already existing list, I need to create a new list node element and then throw the currently existing list as the next pointer to that new cell. So how's that going to work? So I want to creates a new ListNode object to hold a concrete string, add a reference to self to be the next pointer of the new list node. So I'm going to take a copy of the existing list and append it as the next pointer to my newly created list node. So how's that going to work? Well, conveniently, I can just do an anonymous constructor. So I'll just say I make a new list node here out of the blue, and then again, there's no like default constructor on my new list node. I'm going to call that init method where I pass in the new string as input, as well as a copy of the self pointer to be then to be put into the next pointer of that new node. And then again, in Cool, whatever this is, that's the return value. So this newly created list node with the new string put in and the existing list as the next pointer, that whole thing gets returned as the list back from the insert method. So that's what we want. What that means is every time I call insert, I get a whole copy of the newly updated list back as a return value. Okay, and I'll note that explicitly here. So return a copy of the, well, it's not really a copy. Return the newly created list node object complete with the old list as stored in next pointer. Cool. All right, so that's the insert method. We don't really have a way of testing this quite yet, so maybe we should spend some time actually testing this. Now, unfortunately, we have a few of these methods that aren't really implemented yet, so let's comment those out for a second so that we can work on testing if we can actually insert things into this list. And so here's the way that we're going to do this. We want to complete our print function so that we can print elements that are stored in the list, and then we'll go down back to our main method and add some elements to a list. So let's try and do that. So what am I going to do? Ordinarily, if I'm going to traverse a linked list and print out all of the comments, you may have done this before, where you have like a while, like iterator is not null, print out current elements, and then iterator plus or whatever. Again, we don't really have a way of checking is the iterator null or are we at the end of the list. That's where this isNill helper is going to come back into play. Remember, when I insert things into the list, it's going to be a concrete list node object. In list node, isNill returns false. But at the end of the list, I'm going to have this kind of empty list object where isNill is true. And that'll be helpful because now I can just use that instead of a typical null pointer check. So how's that going to play out? Well, I'll just say if isNill, so if I'm at the end of the list, then I'll just do a new line to have the end of the list. Else, I'll do a few things, and I'll have a block here because I want to do a couple print statements. So I'll say, well, I'm going to output whatever is in the current cell, and then I'll output a comma and a space so that I can have some separation from the next element. And then, and this is the kind of critical piece here, there's not really a loop here that we're doing. Instead, we're just going to have a recursive call, and we're going to say, well, whatever the next element in the list is, go ahead and print whatever that is. And then it should reach all of the elements in the list. And fortunately, like there's not multiple recursive calls, so this should be linear time, although it will be wasteful in space, but that's okay. All right, so let's go back here to our main method and now kind of update or create some code to actually test out this list. So I had all this code before for printing out edges. Like, sure, we'll just keep that around for now, but here's what I want to do. I want to have some type of list object that I can add elements to. So outside of my while loop, perhaps up here in this nice let expression, I'll add in another variable to create. I'll have my list, which is a list type, that will eventually store my all the elements that I want to put into this list. So how's that going to, what's that going to look like? I will just have a new list constructor, and that'll just create one of these nil objects that represents an empty list. And that'll just be available to me. And now, in my list, I'm going to add these elements just to kind of test what's going on. I'm going to have my list.insert, and I'm going to put in the source, and then I'll also put in, as a separate element, the destination. And then at the end of this loop here, afterwards, I will do mylist.print, and I should hopefully print out all of the objects right before the hello world string. Let's see if that works. It does not. All right. So it has a complaint here about the print method. Oh, we need a phi to, or a phi to end the if expression. All right, now I have unbound identifier next. That is probably quite right because I called it n instead of next. Great. So why don't I have n.print, and then here as well, my list. So I have created my list up here. Unbound identifier my list. So that would be on 112. Oh, I see. I see. All right. So remember, everything in Cool kind of does one expression at a time. So in this let expression, I have one expression, which is the entirety of this while loop. And so after the loop ends, I no longer have my list in scope. And so what can we do to make that better? Well, there's two things. So I could add a block here, which we could make work. I'm tempted to just make an attribute out here where I just say my list gets new list. That's an attribute, and now I don't need it here in the let expression. And I think that should work. All right, good. So, well, all right. So it's reading in the list, but it is not printing anything. What could be going wrong with our list? So I wanted to print out all the... Oh, I see. All right. So remember, what I said earlier was the insert method returns a new copy of the list. It doesn't actually change anything in my list. It makes a new list and then returns it. I'm not doing anything with that return value. What I need to do is update my list with whatever that returns. So my list gets updated with the newly created copy of the list that has the new element in it. So store, or I should say, overwrite my list with results from insert method. So it creates a new list, we have to put it somewhere. We're going to overwrite my list. Awesome. So now, again, our input was ABAC. I've created now a list and printed it. It's backwards. That's part of the nature of the way that the list is created. But that's okay. Or we'll go through later about how we might reverse the order or do something like that. There's also code for doing an insertion sort in some of the hint zip package. But that's okay. So we've read in all of the cells into our list, and now we have a nice list. Sounds great. Unfortunately, our original goal, recall, was to create a map of lists. So we are going to map vertex names into a list of all of the child vertices. And so we still need our class implementation, We also should technically still finish up the implementation of these methods that we did not finish. So let's do that too while we're here for completeness. So I want to be able to remove elements from a list as well. So how is that going to work? There's two ways to think about this. So in our abstract list class, which represents an empty list, if I want to remove something from it, well, there's nothing to remove because I'm in the empty list. I will just return self and say, well, you know, there's nothing to remove. We're all done. Where it actually matters, or what the actual implementation is in the concrete ListNode class. And how are we going to approach this? Again, there's not really a for loop. We're dealing one node at a time, so there's going to be some recursion here. We're going to recursively call remove until we remove the appropriate element that's specified as the search parameter. So we have to think about how that's going to be done. So just in the comments here, you know, if I insert a few nodes, if I have, you know, A, B, C, that's going to be, you know, list node of A with another list node of B with another list node of C with a list element at the end that represents the nil. If I want to remove an element in my list, well, I'm going to start at the first element. So suppose I want to remove element B. So I want to remove element B. How's that going to work? Well, I'm going to start off at the head of the list. That's A. That's the first element. I need to check. Is the element that I'm removing equal to whatever's stored in this list node? No, A is not equal to B. And so what I'll do is I'll just return a copy of the list where I have called remove on the next pointer. So I'll say, well, does A equal B? No. Call next dot remove. So I have to remove of B. So I have to call it recursively, still passing the same parameter. And now on the next list node, I'll say, well, does B equal B? Yes. So now to remove the element, well, what will I do? I want to return a copy of the list with the current elements removed. I'll just return next, right? So I'll just say, well, I'll skip over this element now that I want to remove it, and I'll just return a copy of the next pointer, and that way the recursive call, when it returns, the calling function gets a copy of the list where it just skips over a single element. So that's what we're going to do here for this implementation. So, well, what am I going to do? Well, I'm going to start by just saying I'm going to start by getting out of this comment space. That would be helpful. All right. So here in the remove body, I am going to call next.remove of search. So I'll just call it. By the way, this should be a block. So I'll add in these extra braces. So I'm going to just recursively call next.remove. And that'll be the first thing that I do. I just go down the list and get a copy of the rest of the list with whatever elements might need to be removed. And I'm going to put that in my next pointer. So again, just recursive call, and then along the way, if elements get removed, they'll be skipped over, and then that gets returned finally by remove itself. And so this next pointer will get updated with a version of the rest of the list with all of the elements that needs to be removed, finally removed from it. Our sort of base case, though, is if the search elements, or if the search parameter is equal to S, that's the value that's stored in this current list node, then that's the one I want to remove, so I'll just return a copy of the next pointer and skip over this current node. If not, then I'll just return a copy of whatever's already here and be on my merry way. And so that's really all we need to do for the remove implementation. to kind of get this working. All right, so why don't we test if that works? I will re-comment out contains here and make sure that we address syntax errors that we totally need to. We're not in a block here. We don't need the semicolon. More of that. And then we also have a thing on 82 here. So I have a problem because I didn't, same issue, didn't terminate this one in the semicolon. Unbound identifier next. I did it again where I have next instead of n. I should probably be smarter about variable naming. In fact, why don't we actually just do that now? Let's search for instances of n here. Come along here. And I'll just rename this to next, next, next. And is that all of them? All right. All right, great. So, so now we're back to a point where it's like compiling again. But let's test this remove method. So now that I'm all done with, so after I print everything, let's say let's remove element B. Just it's one of the elements that was in the list here. We'll just hard code that and say mylist.remove B. And then we will print out the list again. And by the way, remove also returns a new copy of the list. We need to overwrite my list each time we use this. Lexer invalid character single quote. I totally buy that. Excellent. We can only use double quotes apparently in Cool. Wonderful. So I want to fix this so that there's a new line. And great. So look at that. I have a thing where I got all of the elements inserted into the list from the standard input. I removed one of them, and now the updated list is great. All right, so the remove method seems to work. So bravo, we did it. All right, so let's go back to finish up our implementation of list here, where we have the contains method, which is up next. So what's in contains? First, I want to document this. So list class is an empty nil list, therefore nothing to remove. All right, so that's why we're returning self there. But for contains, how is contains going to work? So as before, with contains, you know, we are going to kind of try to go through all of the elements in the list and return true if we ever encounter the element in question. And so we're going to have some way where we have to check, are we at the end of the list? So we'll have some is-nil check. And then we'll also have kind of a content check where we say, well, if the element's value is equal to what we're searching for, then we get to return true. You know, otherwise we'll, if it doesn't, then we'll just keep going through to the end of the list. And so this is another recursive function where we're going to recursively call contains until we either have our base case where you know, is nil is true, in which case we reach the end of the list and we get to return false, because that means the list doesn't contain what we were looking for. We hit the end of the list. Otherwise, we'll have our other case, which is our other base case, which is s, the value that's in the cell equals to the search parameter, in which case we just return true. Otherwise, our recursive case is just call next.contains of the same search parameter. All right, so what is that going to look like in code here? It is just one expression with a nested if statement. So we'll have an is-nil check. If is-nil, then that means we hit the end of the list and never found what we were looking for. So we have we return false. And just, I guess, to make this more readable, we'll do it this way. Otherwise, we're going to check if the search parameter is equal to the value contained in this cell, then we get to return true. And again, I guess for readability's sake, I'll do it this way. Otherwise, I get to call this function recursively. I will return whatever the next pointer is, I'll call contains on that with the same search parameter. All right, and then that's it. I'll close off both of my if statements here. So again, is nil means we hit the end of the list. Otherwise, we're in a concrete ListNode object. And remember, because we're inheriting from this list class, which is where this contains method is defined, the ListNode class will inherit this method. Is_nil will be false for the ListNode class, in which case this branch doesn't execute. In the ListNode class, we have access to the search, well, to the parameter certainly, but also to the cell, the cell's value, and then we can do this recursive next.search call. Okay. So let's test that to see if it works. First, let's see, does it even type check? All right, so there was no compilation issues. And so now down here at the bottom, we're going to, after we print out hello world, why don't we do it here? So if, we'll have an if check here. So if my list.contains A, then I'm going to print out like found A, else outstring no A, no AI, also maybe. All right, so we'll have our contains check on an element that's in the list, and now also, just for good measure, I'll check for something that doesn't exist. So I'll say, is Z in my list? If it is, then found Z. That would be a problem if that returns true. Otherwise, we're going to say no Z. Now let's see, does that work? Sadly, we need to add new lines here. All right, just to make it more reasonable. And then, okay, so great. So we were able to find A, so it contains A, and no Z. Great. We didn't find any Z. I could certainly use some Z's. All right, so our contains method seems to be working. Awesome. What next? So at this point, we have implemented everything here except for size. All right, so let's do size next. In a recurring theme, this will be a recursive function where basically we return 1 plus whatever the size of the next element in the list is. Eventually, we'll hit that base case where we're up here where if we're at the end of the list, when we call size on that list, it'll be 0. That'll be the end of the list. And then we just add that sort of one by one to all of the, to each invocation of the size method kind of adds 1 to this running sum that will build up. And so recursively call size on next pointer, add 1 each time. So how's that going to look? Why don't we just return 1 plus next dot size, and that should be it. I believe we can also test that to see how it works. So let's do that real quick. So we'll have some text here to help us. So size of list, size of my list, and then outInt is a method for printing integers, where we'll say mylist.size, and then again, to complete it, another new line. Let's see, does that work? Okay, great. So we have 4 elements in our list. Size of my list is 4. All right. So at this point, we have finished up with most of our functions here. I think there was one other that we got remove. Okay, so I think we got all of them. There's a few more helper functions that we might come back to later, but that's all of the list items. So now we have a functioning list interface. It only took us an hour and 15 minutes. Okay, all right, so this will, maybe we'll need timestamps for this video. All right, so we will continue then with the next part, which is a map implementation. What could go wrong? Fortunately, it's a lot of the same type of concept. Now, for our map implementation, let me make some space down here. Map implementation. It's going to be a lot like the list. So this is basically going to be a list except with more attributes and different insert functions. We're going to have a key attribute. This will be the key, which is a string. This will be like how we're organizing the map. That's, I'm going to map the key onto something. I'm going to have something, well, we'll just call it elements, which is going to be a list. Remember, I want to map vertices, which is a string, into a list of vertices, which are the children. That will be present as well as an attribute, and then the other thing is we're going to have a next pointer. Again, we don't really have any type of collection map or built-in list structure, so we're just going to have another next pointer that will go to the next item. And the way that this is going to work is we're essentially building up a list of key value pairs. We're going to have a list where I have a key and the associated elements. And when I go to search through this map, it's going to be a linear search, so it won't be as quick as like a Python dictionary or a traditional map. But I'll just go through and I'll search. Well, if I want to get the list of child vertices for a particular vertex, I just linearly scan one by one until I find the map cell that contains the correct key, and then I'll have access to the elements list at that point. So I'll have all of these things. I'll have accessor methods as well for them, accessors for each of them. I want to have a contains, which will take in, a string that will tell us if a key exists in the map already. That'll be useful. Again, if we're going to insert multiple child elements associated with one key, then I need to check, is that key already present in the map before I create a new map cell for it. That'll come into play later. I want to have an insert method, which will take a key value pair and update the correct map instance with that new value. So I want to look up the list associated with a key and append the value to the list associated with that particular with that key. I want to have a Vim misbehaving slightly. All right, so I want to have a remove method, which will remove a key value, a specific value from a specific key. So that's if I want to remove one node, one child node from the list associated with one key. That'll be what my remove method is for. I want to have a get method that will return the elements list associated with a particular key. And then I want to have, again, a helper print method to print out each key value pair. All right. What could go wrong? So, similarly, we're going to have a map that's an abstract class, and then this map node thing that's the concrete map instance. That'll help us keep track of whether we're at the end of the map, and if we, again, this matters for when we insert new keys into the map. We need to make sure we're at the end of the map before we do that. And so we'll also have this map node thing that inherits from map. So why don't we get started by actually writing out our new map class. So we'll have class map. Again, I'll inherit from IO for good measure, just so that I have access to those outstring functions. I'm going to have a string as a key. I'm going to have these are semicolon delimited. I want a elements thing, which is a list of strings. I'm going to have a next pointer. I'll actually call it next this time, which is a map. As before, I need an isNil helper, which for my abstract class, I'm just going to call true. I'm going to have accessors, so I'll have key, which is a string that returns key. I want to have elements, which is a list. It just returns elements. I want next, which is a map, and that returns the next pointer. All right. What else do I need? I want a contains method, which will take in a search string as input. This will return a bool. We'll implement these later once we get back to our concrete case. Well, actually, we can do it now. For this one, like as before with the list one, so I'll check. Are we at the end of our map? If we are, then we've reached the end and that key doesn't exist. Otherwise, if the key is equal to the search parameter, then we'll return true. Otherwise, we will return whether the next element in the map contains that search term. So we can implement that. It doesn't really depend on anything else. That'll be just fine. Inserts. I want to have an inserts method that takes in a search string. So this will be the key in which I want to associate a new value. I'll have a new value to add, and that will return a new map, as we've already seen with the list. It's kind of the same concept here. We'll come back to this after we finish up the concrete map node as well. I want a remove method that will take in a search string as input, and then a value to remove. It will return a new copy of the map as well. Kind of the same deal that we saw already, just a little bit more checking because we have this elements list in addition to a single string here. We'll have a get method where, again, we take in a search string as input, and we return a list. We're going to get the elements list associated with a particular key value. And so again, this is one of those things we can just do now really quickly. So if we're at the end of our map, then we're just going to return a new empty list because there's nothing there. Otherwise, we're going to check if the search input is equal to the key for this particular object, then I'll just return back whatever elements is. Otherwise, I'll check, does the next thing contain the same search key? Does the next thing contain the search key? And that'll be, I'll end my two ifs there. Now, we can also do a print implementation real quick as well. Kind of similar to how we did it with the list already. There's more information now. So we have a whole key and an elements list, and we want to print out both of them for each entry in this map. So how's that going to work? Well, as before, if we're at the end of our map, then we're just going to print out the new line, no problem. Otherwise, we're going to do a few things. Just to make the output look nice, we're going to have this format where we say, well, the key at this particular cell or at this particular entry in the map, we're going to have that key map onto whatever the list is. Fortunately, elements is just a list. We already have access to a print method that works for our elements list. We'll just print that out, and then, as before, this is a recursive function. We're going to recursively call print on the next element in our map. All right? And that, I need to finish the if there, and I shouldn't actually need that. All right. and this should bring me back there. All right, good. So, so that's our abstract map implementation. Again, we need to fill in a few methods, but we need to do, as we did with the list implementation, we have to do a map node. Again, fortunately, this will be a pretty short implementation, just like we saw with the ListNode implementation. So we'll just do a map node, which inherits from map. And here, what we're going to have is, first, our isNill helper is a Boolean that returns false for the concrete case. And we're going to have an init method. So as before, with our init method, the way that we're expecting to have this called is init will be called when we need to insert a new key value pair into the map. This method is called like when the specified key has never been placed in the map before. So this is, this is for the case where, I want to insert value, insert key A, value B. So if I have the edge A to B that I want to insert into this map, if I have a totally empty map, key A has never been placed there before. If I then have a second thing, so if I want to insert another edge, A to C, A should already be in the map at that point, and we wouldn't need to call init. Init is only for the case where we have never seen a particular key before, and we're going to create a new map node to store that particular key and then an associated list of values. But the usual case then is the user is just saying, well, insert this key value pair into the map, and so what we need then is, what we're expecting then is, we have a key, a value to insert, and then, again, if it's an already existing map, we need a reference to whatever the rest of the map is. It's just like the list implementation. So our init method is going to take in a search string, so whatever the new key is. That's going to take in a value that needs to be inserted into the list, and then it's going to have some, like, the rest of the map that gets passed in as well. This is going to return a map node type, and what it'll just do a couple things. First, we're going to update the key for this. That's the attribute for this particular map node object. We're going to overwrite it with whatever the search string is. We're going to create a new list. So elements is now some new list that is going to contain, I don't need the parentheses actually. It's going to contain just an empty list. And now that we created that list, we will just immediately overwrite it with, as we did before, we're going to insert whatever the value is into that list, and then it should contain that single element, and then we're going to say, well, the next pointer is whatever the rest is that has been specified here. And then finally, this has created a new map node that represents the newly created key, and it should have in its next pointer whatever the existing map was. So we'll just return a self pointer, again, as we did with the list implementation. And that's about it for the map node. So now that we have this, now we can go back to fill out some of the other methods that we had in the map class here. In particular, let's do this insert method. The distinction between the map and the list in this context is because the user of this map type, they're going to be specifying like, oh, inserts the key value pair AB. So if I want to associate the value B with the key A, I need to check, does my map contain that key already? If it does, append the new incoming value to the already existing list. And so now there's this extra step where I have to check, is the specified search parameter already in the map? If it isn't, then I create a new map node, If it is, then I update the existing list for that existing map node object that's already in the map. So I'll have to do a couple things. So first, the easy part, I will say if is nil. So if we've already reached the end of the map, then we know for sure that the key isn't already in the map. In this case, we need to create a new map node object and initialize it with search, the search parameter, the value, which is the value that we want to associate with that key, and a copy of self, so whatever the existing map already was. So that's all we need to do here. We'll return that. We'll return the new map node here. Otherwise, if we haven't reached the end of the list, we need to check, does the key already exist in our map? So we'll check if the search parameter is equal to the key. So if the current map node that we're looking at, if its key matches what we're trying to insert in. So if we're trying to insert a value into a key that already exists, well, then we want to check a few things. What we technically all we need to do is just say, well, I'm going to overwrite elements with. I just want to insert the new value here for the. I want to insert the new value for the list that already exists here. Now, that could work fine. However, I hinted earlier that maybe we don't want to have duplicates. We may as well do that now. So what I want to do here is to check instead if elements.contain. So if that value that we're trying to insert already exists in this particular list, then I'll just say I'm going to return self and not do anything because I don't want duplicates in the list. Otherwise, if that doesn't exist in the list, I will insert elements. I will insert the new value into the elements list, and then I'll return the updated copy of this particular map node, like that. So again, just to recap what's happening, need to check if we're at the end of the map. That means we never encountered the search key. What this means is create a new map node object for that key and insert the value into the new list associated with that key. Otherwise, if the current node, so if the current node's key matches the search parameter, that means we're adding the value to the already existing elements list for that key. So that means just append the value to the existing elements list. Great. If the current key doesn't match the search parameter, then recursively call insert. Right? So just keep going to make sure that you don't have this key already in the list. For this implementation, no duplicates. So here we're just checking we're going to create a new map node if we reach the end of the map. If we encounter the key along the way during our traversal, to make sure that there's no duplicates, we're not going to do anything if the value is already in that list. Otherwise, we're going to add it to the end here. Otherwise, what I need to do is to say, next.insert search value. And in addition, remember, this is just like with the list implementation, I need to overwrite the next pointer with whatever the updated map is for the subsequent map nodes remaining in this map structure. And then again, after I do that update, I need to make sure that I'm returning a whole new map node, the newly updated map node. So I'll just make a self as the return thing here, as the return value here. All right. So that should be it. So I need to end this if. So this goes with this one. This goes with this one. And so that should be all done there. We should probably test this at this point. So let's get rid of that. We'll comment that out for now. And let's try and actually use this map real quick, just so that we can make sure that we're testing frequently as we add new features. As before, it was just easier to put a new attribute up here. I'll just have my map, which is a map, up here as an attribute for main. And I will say here, let's say, after, we'll eventually be adding edges here when we're reading things in. But for now, after all this list business, let's say I want my map to get my map.insert. I'm going to say A and B. I'll have a few of these. A goes to C, A goes to D, D goes to B, and we'll see how that goes, and we'll have my map.print just to see what it looks like, and probably syntax errors. Oh, of course, I forgot a feat. Unbound identifier elements. I have used element instead of elements somewhere. Here we go. All right, and look, it's actually working. So I've inserted for key A, I've inserted 3 elements. So just to remind you what I've hard-coded into here. So I did 3 inserts on A. So I conceptually in this eventual DFS implementation, I have 3 edges. A goes to B, A goes to C, and A goes to D. That is reflected here with a 3-element list associated with the key A. And similarly, I only had 1 insert for the edge D to B. That is reflected as a 1-element list associated with key D. All right, so our map insertion seems to be working. For good measure, let's also do this remove method wherever I put it. Okay, so I commented it out here. What is that going to look like? Conceptually, again, I want to check if we hit is nil. So if we're at the end of the map, that means we're done. We never found what we needed to remove. So just return self and don't do anything. Otherwise, if the search key matches, if the search parameter matches key, then remove value from the associated list. So we already have the list remove function, so we'll be using that. Otherwise, I should say, in addition, we're also going to remove the we're going to recursively call remove on the next element. So recursively call remove on next. All right, cool. So if we have is nil, then that means we've reached the end of our map. There's nothing to do. We're all done. Otherwise, if the search parameter matches the key for this particular map node, then we're going to overwrite elements with a copy of elements with that specified value removed. After we're done with that, we return the updated copy of self. That's what we do there. Otherwise, so if the search key doesn't match, or I guess we won't have duplicates for the keys, so this should actually work fine. So if it doesn't match, then we'll do next.remove for the same key value pair. And then, as before, we'll just remove self. Technically, I should be doing next gets next.remove, and then I return self. Then I'll end my if. I need end of an if here to finish that up, and that should also work. And so now, again, maybe I'll just add in one more here. A goes to E, and then I'll have my map gets my map.remove from key A. I'm going to remove C, kind of right in the middle there, and I'll see what happens. Ho ho, it's working as expected. So remember, I added in A goes to C, and then I removed it here at the end. That is reflected here, where I just get to I skip over C in this output here. So it seems to be working. So I have now a map implementation that seems to be surprisingly complete, given where we started, and given that we have like no primitives for building any of this stuff. So we have a map implementation. Are there any other functions that we forgot to implement? So we have all of the accessors, remove, get, we already did. It just returns the appropriate list. All right. So now we have a functioning list. Let us actually remove all of this testing code that we had, and let's actually do something with it. So remember, we started this video by saying we wanted to do DFS, and here we are an hour and a half later. Now we're prepared to actually do DFS. How is that going to work? Well, first thing I want to do is to make sure that all of the edges that are provided as input get put into this map structure. So what will that look like? Well, we have my map already. Rather than using this list thing, we're going to say my map dot insert source guest, and that will put all of the edges into our map. Now, after we're done, so this is done reading inputs, why don't we just print out the map and see what happens once we're provided this graph as input. Great, right? So remember, our graph had two edges, A goes to B and A goes to C. Well, it's printing that out. It doesn't seem to actually be, oh, I see. We need to update my map with the result of insert. Up arrow more. Okay, great. So remember, I have two edges in my graph. A goes to B and A goes to C. That is reflected with this map that has one key and a two-element list there. Great. Maybe I should have a more complicated graph, and this will also help since I want to test an eventual DFS implementation. Why don't we just go check if this ever loads? All right, so let's go check, not Dijkstra's, but maybe depth first search. DuckDuckGo.com will work better, apparently. This is for, depth first search. Which one shall we use? Do we like any of these graphs? All right. So let's check it this way, or why don't we do it this way? So let's try and input a graph like this. So like we'll say it's the wiki graph, and we'll just input in these graphs kind of like manually here. So I have 1 goes to 2, 1 goes to 7, 1 goes to 8, 2 goes to 3, 2 goes to 6, 3 goes to 4, 3 goes to 5. I already have 1 goes to 8. I need 8 goes to 9, 8 goes to 12, 9 goes to 10, 9 goes to 11. Let's see what happens if I bring in this wiki, and it seems to kind of get all of them, right? So again, node 1 goes to 2, 7, and 8. 2 goes to 6 and 3. 3 goes to 5 and 4. 7's not there. 8 goes to 9 and 12. Yes. And then 9 goes to 10 and 11. All right, cool. So we have a representation of our graph now. So let's bring this back to our code. And let's actually implement, let's actually do the purpose of this helper video, which is to do a DFS implementation. So we're going to just make a new method and bring up and actually, kind of implement it. Now, fortunately, DFS is not that complicated to implement. Indeed, there might be pseudocode that we could potentially borrow from, where we have some sort of visited list. We're going to make sure that we mark things as visited when we encounter a new node, and then we're going to check all the neighbors. Conveniently, we can get the neighbors easily through our new map structure, and then we can just recursively call DFS on the graph with each of the neighbor nodes and eventually visit everything. Sounds great. Let's actually do it. So our DFS method is going to take in some graph as input, which will be our map that we just formed. It's going to have some visited list, which will continue to get updated along the way. And it's going to have some vertex that we want to start at, which is just a string. This is going to return a list. This is the nodes that we're going to visit. And we're going to have a little block here. Now we're going to say, if the current vertex that we're considering, so visited, vertex, so if not visited dot contains, remember we implemented that on purpose, if our vertex is not in the visited list, then we're going to do some stuff. For good measure, we'll say, well, we're going to visit some node. We'll say vertex, and then we're going to say all new line. And then after that, so like once, if this is a node that we haven't visited, well, we're going to then update our visited list. We're going to say it is visited. So visited dot insert of that vertex that we're currently visiting. Next, we need all of the neighbors. We're going to visit all the neighbors. So we're going to say, well, let neighbours is going to be a list. So we're going to get a collection of all of the neighbor nodes. We're going to get this from the graph. So remember, we had this get method, which given a key will return a list of the elements associated with that key. So this is going to get us all of the child nodes associated with the particular vertex. Okay? And we have to, again, from the Wikipedia article, for all of the neighbors, we're going to visit them recursively. So we also need to do a loop here, which means our favorite, a done Boolean variable that's initialized to false. We'll do it this way. So we'll say, while we're not done, we're going to loop, and we're going to say if we're going to go through our neighbors our neighbors list one by one. So remember, the neighbors list it's one object and then it has a next pointer. So we're going to check, if we're at the end of the list. So if neighbors.isNil, then done is true. Otherwise, we're going to visit each of these neighbors in turn. So we're going to say, we're going to update the visited list with a recursive call on the same graph with this, the newly updated visited list. We're going to pass that in, and we're going to get the value contained within this particular neighbor cell. So whatever neighbor we're currently looking at, we'll get that value. And then we're going to update our neighbors pointer. We're going to do neighbors gets neighbors.next. And that's it for this if statement. And then we're going to do pool to finish. And then, of course, this is an expression, the end of the let expression in our block here. We have to end it with a semicolon. and then we return back up here where we have to do an else, where we're just going to return visited. So, if we're finished with everything, if there's nothing left in visited, or if we've already visited everything, we just return that. And then finally, eventually, we just return visited itself. Seems too good to be true. Let's see if this even compiles. I seem to have put in a single quote somewhere. Double quotes for everything. All right, so now that we've implemented DFS, we hope, let's check if it works. We'll call DFS on my map, which is what the kind of like edge list mapping thing that we just produced. We will call it on a new empty visited list, and we're going to start from this, again, what we borrowed here. It's node 1, so we'll say starting at node 1. Now let's see what happens. And look at that. We eventually visit all of the nodes. Now, at this point, we might be wondering, like, well, what can we do about, is this the correct order? Should we be doing something different? That might relate to where where we put the print statement and so forth. This is quite good to start. I think at this point, since this has been a 2-hour video, I'll probably call it here and continue in a different one, so where we can talk separately about sorting. All right, thanks everyone.